This is John Pillar. I will be presenting a method of approximating the shape a chain takes in space using a method I call the discrete chain link method. This video is being made to fulfill the final exam requirements of MET 503 for spring 2013. A chain will, by nature, hang in the shape of what's called a catenary, or a hyperbolic cosine, when fixed at two parallel points. As seen here in the graph, this shape will be used to measure the accuracy of this method's approximation. Galileo predicted this shape to be a parabola. While close, it's not exact. In 1671, Robert Hooke presented to the Royal Society the true and mathematical form of this shape. The catenary minimizes the potential energy of the chain. So if we minimize the potential energy of the series of triangles that we're approximating, we should be able to predict the lowest y position and the centroid of the hanging chain. As seen on the drawing, each chain link is the length of delta L. This length is the hypotenuse of a triangle. So if we begin with a position of -1, 0 and make our chain about those zero axes, we can successfully predict that the next point in space with the equation on the top right on the screen for the x and y positions. PE is solved with the equation of potential energy equals mass times gravity times height. We're going to factor out the mass times gravity portion and distribute it evenly amongst the chain by using the ratio of the number of links divided by the length of the chain. And then we'll also divide that ratio by 2, because we're only predicting on the left side of this chain. Boundary conditions at the lowest point of the chain will have an x position of 0, and each angle of every triangle is going to be a design variable. By using the minimize function in MathCAD to solve for each angle and the potential energy, we can take those angles and solve for each successive xy position. And then we can plot that shape against the known catenary shape. And we have that here. It's a 30-link chain, and visually it matches the exact shape fairly close. The y prediction is within a ratio of 1.018, and so is a centroid. When the predicted x position values are used in the exact catenary formula, we end up with a ratio of the y positions of 0.946 to 1.018. The potential energy also is 1.05, so we're good there, and the overall model is sound. So there it is, a hanging chain using the distinct link method. Each one of these links are the same length. I don't have a chain, I have paper clips. But you get the idea. Our method showed sound. We were able to predict all the y locations. We were able to predict the centroid, and we were able to predict the potential energy along the way. So any questions, please feel free to email or go ahead and ask questions here in the class for this presentation. Thank you very much.